Section 7.4, solving nonlinear systems of equations. So first off, that systems of linear equations, we only had three possibilities. We could have no solution, one solution, or an infinite number of solutions. When we're dealing with systems of, we can have many other types of possibilities. Okay, so I'll actually look at some examples. Some of the techniques that were available for solving systems: graphing technique, substitution, elimination, the matrix methods, and determinants. Obviously, trying to draw nonlinear systems, trying to draw something that's nonlinear, finding where it intersects another nonlinear graph is going to be extremely difficult. And so basically, we don't use the graphing technique. Similarly, the matrix techniques and determinants are really not applicable for nonlinear equations. So we'll just eliminate those. Those are not really techniques that we can use. But substitution and elimination, those are possibilities. So we can use those techniques. If we can use elimination, we'll use elimination. Otherwise, we'll probably have to use substitution. So if we're able to use elimination, we try to use it. In this case, there are not as many situations where we can actually use elimination as compared to the case where we looked at the systems of linear equations. But if we can do elimination, we do. Otherwise, we'll do substitution. Oh, good. Scrolling. Ooh. I'm sorry. I just saw the... It's lagging for you. Yes, it is. Very much so. Okay, so systems of nonlinear equations. They can have many more differing types of number of solutions as compared to systems of linear equations. So let's say if I have two parabolas, we can actually have 0, 1, 2, 3, or 4 solutions. So if I look here, say I have these two parabolas, they can intersect at no places, so I have no intersections, or they can just intersect at one place, so there's one solution, or I can intersect at two places, two solutions, or even three places, three solutions, or in this case, 4 different places, so 4 solutions. And that's really about it. Well, you can have number of solutions, I guess, if you had the exact same. I guess I should do infinity. If it turns out that the two parabolas are the same, then you can have an infinite number of solutions. So maybe I should say 4 or infinity. Oh, geez. Okay, so 4 or infinity. Okay. So those are the possible number of solutions. Okay, so let's do some examples on page 708. Solve each system of equations using substitution or addition for real values of x and y. So when we solve this, we'll only be interested in real solutions, not in complex solutions. Only if you were dealing with math past this, would you be concerned with solutions that are not real, such as only integer solutions or solutions in some sort of, finite field or complex solutions, things of that sort. For us, we'll just be interested in solutions that are real. Okay, so actually maybe I should call these something. So let's call this R1 and R2, just so I can talk about things. Okay, so problem 18. X squared plus y circle, y equals x squared parabola. So I have a circle and a parabola. Maybe I should just say that. So this is a circle. And R2 is a parabola. So I'm going to try to intersect these two and see. Let's try to solve this and see where they intersect. Okay, so in this case, let's use substitution. So let's substitute. So R2 is solved for. Y has already been solved for X. So I'll use R2. So I'll substitute R2 into R1. Okay, so let's do that. So I have X squared plus Y squared equals 20. And so I have X to the fourth plus X squared, subtract 20 from both sides of my equation, minus 20 equals 0. So let's try to factor this if possible. And so this factors into X squared plus 5 times X squared minus 4. This is a nice monic, well, it's actually quadratic in X squared polynomial equation. And so I'll just put down X squared here. I want two whole numbers whose product is 20 and whose difference is 1, so 5 and 1. Drop down the plus times minus is minus. So now I have X squared plus 5. Let's factor the X squared minus 4. It factors into X minus 2, X plus 2. Let's set each factor to 0 and solve for X. Since this is an integral domain, we can use the zero factor property. Subtract 5 from both sides. Add 2 to both sides. Subtract 2 from both sides. Well, we can't have that X squared is equal to negative 5 if I'm only looking at real solutions. So now let's use R2 to solve for Y. And so I have that Y is equal to X squared. Y is equal to X squared. Let me do another page. Okay, now it's moving. And so I have Y is equal to 4. Here, Y is also equal to 4. So therefore, I have two solutions. When you actually do a problem that involves nonlinear equations, you must write them as points. And so the coordinates are 2, 4, and negative 2, 4. So you can't just sort of say X is equal to 2 or whatever, and X is equal to negative 2. That's not sufficient. You have to tell me what the X and Y coordinates are. So I have two solutions. Let me do problem number 27.
I have a question.
Yes.
I didn't quite hear why we cannot do the negative 5x squared.
You're gonna have to talk louder. Could
I
you please
said,
repeat?
yeah, I said, why I did not hear your explanation of why we can't use negative 5x squared in the
Oh,
article.
oh, oh. Okay. You didn't hear why we get rid of this solution. It's
Yeah.
because we only want real solutions. And so we can't have a square of a number, a real number, being negative. So since we only want real solutions, and so we only want real values. And so since we only want real values, then we're going to get rid of solution.
Okay, thank you.
Was that your question?
Yeah, it was. I just did it kind of, my internet is not as good, so it was kind of lagging and I wasn't
I assume that
understanding.
answered your question. Okay, let me do problem 26. And so let me call this R1 and let me call this R2. So problem 26, I have 9x squared minus 7 y squared equals 81. So in this case, R1 is a hyperbola. And we have R2, x squared plus y squared equals 9. Well, that's a circle. So we're going to be intersecting a hyperbola and a circle. So we could have 0, 1, 2, 3, 4 solutions. So we'll have to see which of those this is. So let's take, I guess let's try to eliminate y squared, y. So I have R1, 9x squared minus 7y squared equals 81. I have, let's multiply R2 by 7. So I have 7R2 is 7x squared plus 7y squared equals 63. And let's add both of these. And so I get 16x squared. The y squareds cancel, equal 144. Divide both sides of my equation by 16. So x squared is equal to 9. And so by the square root property, x is equal to plus or minus 3. Well, actually, let's leave it like x squared equals 9 and substitute that back into, let's call that R3. And let's substitute that back into R2. Okay. And so let's substitute R3 into R2. So that will give me x squared plus y squared equals 9. And so I have that y squared is 0. So y is 0. From R1, R3, sorry, from R3, I get that x squared is equal to 9. And so by the square root property, x is equal to plus or minus 3. In both cases, y is 0. And so my solution is just negative 3, 0, and positive 3, 0. Actually, sort of strange that in both cases, my y was the same for both x's. Usually it's not. It just happened to be a coincidence that this happened in this particular case. Okay, so that